Hello students, in lecture 22 of your course Calculus of Variation and Mechanics. In the mechanics part, we discuss the Lagrangian for a double pendulum, and in fact after setting the Lagrangian for a double pendulum, we shall find the equation of motion. Then we'll express kinetic energy as a quadratic function of generalized velocities and certain other related theoretical results. So the first example is regarding the double pendulum. Set the Lagrangian of a double pendulum and obtain an equation describing its motion. So first we see what is the double pendulum. Double pendulum is shown here in this figure B. It consists in fact two rods of length h1 and h2 respectively, and their masses are m1 and m2 hung from a pivot. They are hung over here. The system has 2 degrees of freedom, that is theta1 and theta2. So because the length of both of the rods is fixed, h1 and h2, mass is fixed, the only thing that will vary is this angle theta with the vertical. So let us describe the configuration of the first pendulum here, that is configured by this length h1 and this angle theta. So let us see. In this case, we can have that this distance, and of course this is the x-axis, and we are downward. That's we are considering that this is origin. So when we are moving here, so y distance will be negative. So here this length is h1. Fine. So when we calculate the value of this length here, in fact y1, so y1 is equal to the first this x1. Suppose the coordinates are here x1 and y1 for this part. This is origin here. So first we find x1 is in fact this distance. When the mass is here, then the distance traveled along x-axis, this part is x1. So x1 means perpendicular over hypotenuse is sine theta. So we can say that x1 is h1 sine theta 1. Now we find y1. Y1 is this thing, that base over hypotenuse. That gives you h1 cos theta 1, but it will be negative because it is downward. So for this first pendulum, we are having the values like this. That means if this distance is x1, then from here we are going to find the things here for the second pendulum. For the second pendulum, let this part, in fact the whole distance will be x1 plus this part. So look at this part only, because this we are knowing that x1 is there, h1 sine theta. So exactly in the same manner, if we try to find it out, so this part will be equal to h2 sine theta 2, and similarly the lower part here for y2, corresponding distances y2 will be minus s2 minus this one h1 cos theta 1 plus this h2 cos theta 2. So x1 is h1 sine theta 1 as described earlier, y1 is minus h1 cos theta 1, then the distance x2 is in fact we are calling the whole distance up to this place is x2. So this x2 will be sum of this part plus this part. So this part gives you h2 sine theta. So in fact x2 is this thing. Similarly y2 is sum of the first one and the second one. So that is how we have evaluated the Cartesian coordinates for the double pendulum. Then the kinetic energy will be given by, for both the cases, half of mass m1 x1 dot square y1 dot square plus half m2 x2 dot square y2 dot square. Now these are expressible in terms of the variables theta1 and theta2. So when you find x1 dot, definitely h1 is constant. It will be sine theta, it will be cos theta1 into theta1 dot. It will be, and we'll take the square. Then here y1 dot means minus h1, cos theta means minus sine theta1 and into theta1 dot. So and square of that, substituting these values here, we can obtain the expression for the kinetic energy of a double pendulum is this. The potential energy is V equal to m1gy1 plus m2gy2, and that is minus m1 plus m2g h1 cos theta1 minus m2g h2 cos theta1. In fact, we are substituting the value of y1 and y2 here, so that the value of potential energy comes out to be this. Now you know the Lagrangian of a system is given by L equal to T minus V. That gives you the potential energy here and minus this the kinetic energy over here and the potential energy V here. We substitute the values. So clearly here H is constant, H1, H2 are constant, M1, M2 are constant. So the only variables are theta1 and theta2. So we can say we have the generalized coordinates theta1 and theta2. In fact, Q1 is theta1 and Q2 is theta2 in this case. So we'll have the Lagrangian equation of motion in this way. We will have two equations in fact for theta1 as well as for theta2, because here I is 1 and I is 2. So from this Lagrangian we find all the values del L over del theta1 dot, del L over del theta2 dot, del L over del theta1, del L over del theta2. So all the values can be calculated from this equation 7. So in fact we are having these two equations 9 and 10, and we calculate the values, and after calculation of the value d by dt, del L over del theta1 in fact gives this equation 11, del L over del theta1 gives you equation 12, this gives you 13, and del L over del theta2 gives you 14. Using these equations from 9 to 14, we obtain the final governing equations for the double pendulum. In fact, we get two equations from equation 9. After substituting these values, we get this equation. And from equation 10, by substituting the values from here, we get this equation. So these are the equations of motion for a double pendulum. Now next article is express here the kinetic energy of a system of particles as a quadratic function of generalized velocities. So is it possible? Then we see here, if at any time t the position vector of the ith particle of mass mi of a holonomic system is ri, I going from 1 to n, capital N here. In fact, there are n particles in the system, and let the system is specified by n generalized coordinates, that is q1, q2 up to qn. So this r, the position vector ri, can be written like this. It is the function of q1, q2, qn and the time t. So there are n particles, in fact r1 for the p1, p2 and so on pn, and for corresponding to each of these we have the position vectors r1, r2 and so on. This is rn, and each of these depends on the generalized coordinates q1, q2, qn and the time t. Similarly for all these. So that is the situation here. Then the kinetic energy T, you know that 1 by 2, I going from 1 to n, because there are n particles, masses are mi, for here mass is m1, for particle 2 m2, this is mn in fact. So masses are mi, half into mass into velocity square. Velocity is ri dot square, we get it. So just try to find it out, what is ri dot square. Ri is the function of Q1, Q2, Q1 and T. So we have already done this kind of uh, calculation, that it will be del Ri by del Q1, then del Q1 by dt, because the meaning of this is dri by dt, and this can be written as ri dot we are writing here. So here dq1 by dt. Similarly here it will be del ri by del q2 dq2 by dt. So dq2 by dt will be written as q2 dot, and so on similarly. Further, it is also a function of t. So we write del ri by del t, and here it will be in fact dt by dt. So that is in fact 1. That is why it is not written over here. So this part in the form of a summation can be written like this, plus this part we are keeping separate, del ri by del t. So this is value of ri dot. Now we substitute this value here in the kinetic energy expression. So we get T equal to 1 by 2 summation I going from 1 to n mi, and this is the value of ri dot square. Now we open this square. In fact, this is a square of n plus 1 terms. In fact, when you put the values j going from 1 to n, so n terms will obtain after opening this summation, and one term is here. And when we scale such expression, what do we get? You know, when we have a1, a2, and suppose an plus 1 square. So how you open this kind of expression? In fact, it gives you a1 square, a2 square, a3 square, an square, and all these. So in fact, you can write ai square summation I going from 1 to n. Further, you will have AI, A1, A2, A1, A3, and so on and so forth. So you will have AI, AJ. I and J will not be equal. When equal, that means squares we have already taken, and it is also from 1 to n. Twice of that. In fact, this is twice of 2AB. So in this way, we open this expression. So how we look at the situation? In fact, we will get this part, and this part. So from where this third term we are obtaining a square. Basically, we are keeping it as a square and plus a plus b. So a square means we are talking about this part square, and the n plus 1 term is this one. So when you open this, you are getting this term plus b square. B square means this term a1 square, a2 square, an square. This gives you this one. Then twice of this gives you this term. Then b square means this term. Then you will have twice of the whole thing. This one a1, a2, and up to an, and into this an plus 1. So that is why it is in fact sum of the square of two elements here, a and this is b. So in this way you open it. So we are getting here this type of expression, and from this expression you can see in fact this is combined with this. So that is why we are having only 3 terms here. So using these 3 terms, you can see the expression is like that: 1 by 2 summation I going from 1 to n ham I, and here we are opening this. This is corresponding to this part. This is corresponding to this part. AIAJ means RI, RI, QJ, QL. J and L are not equal. QJ dot, QL dot. So this is corresponding to this part. Further, then when we are having when we are having the square of this, the square of is this part is here, this part is here, this one, and then twice of this into this, we are having this part here, del Ri by del T, this one. So twice we are taking here, so 2 is cancelled out here. So here this is not twice here. So that way, in this way, when you open it, we will get this expression, and in this expression we are having three terms, and we denote the term by certain notations, that we are denoting the last one as T naught, and in this expression this Aj means this term, summation I going from 1 to n, and mi and rest of the things, these are we are calling Aj, and Qj dot is there, so that is why the second term is written like this. Then the first term you can see 1 by 2 j going not equal to L, I going from 1 to n. So here in this part, this del Ri by del Qj, del Ri by del Ql, we are denoting it by Ajl along with the summation I going from 1 to n. So these are the notation we are using over here, and with the help of these notations we are getting T equal to this quantity. Further we are denoting these by certain other expressions. This as T1. In fact, this expression we are calling as T1. So T naught, this is T1, and this expression will be called T2. So in this way, T is sum of three terms, T2, T1, and T naught. So T2 is this quantity, and T1 is this quantity. So here we have expressed T2 as a quadratic function in terms of the generalized velocities. And here T naught is independent of generalized velocities. You can see T naught, the value T naught, you can see T naught is independent of generalized velocities. So in all, if you look at the expression of T, it is a quadratic in terms of generalized velocities, because here you can see Qj dot, Ql dot, this is generalized velocity, and generalized velocity total degree becomes 2. That is why it is a quadratic expression. Further, in particular case, in case of celerionomic system, the time does not occur explicitly into the relationship, and therefore del Ri by del T comes out to be 0. And when this factor comes out to be 0, this part becomes 0, that is T naught becomes 0, and this part also becomes 0, that is T1 also becomes 0. So we are left with only T2, and T2 is equal to AJL Qj dot Ql dot. Now you can see the kinetic energy of a celerionomic system appears in the form of a homogeneous function of second degree, because 1 degree and 1 degree, this is a homogeneous function of degree 2. Now one result is there, we can write, if h be the homogeneous function of degree n, then by Euler's theorem in the differential calculus we know that x del h by del x plus y del h over del y z del h over del z is equal to nh. So here basically T is homogeneous. T is homogeneous, we have seen in the last article. T is homogeneous of degree 2. And what are the variables? Variables are q1 dot, q2 dot, and so on, q1 dot, because it is homogeneous of degree 2 in terms of generalized velocities. So that is why by using the Euler's theorem, extending it for the n variables, we can write q1 dot del t by del q1 dot, q2 dot del t by del q2 dot, and so on, and 2, and in place of h the function is t. So this is equal to 2t. So here we also know that this t is the function of qj dot and t, but in case of celerionomic system we have this as a function of qj and qj dots. Fine. So here in fact from this equation, if you write it in the form of summation, this gives you qj dot del t by del qj dot, because pj we have already proved that is equal to del t by del qj dot, and in fact it is also equal to del L over del qj. So this value becomes P1, this P2, and this is Pn, And in general, when you write this expression in terms of summation, this becomes Qj dot Pj is equal to 2T. So this is also an important expression you need to keep in your mind. The next article here is regarding the conservation of energy. Deduce the principle of energy, the Lagrangian equation in case of conservative force system, or the energy equation for a conservative force system or conservative field. So we deduce the equation. Lagrange's equation of motion for the system of conservative forces is given by this. We have already obtained this equation in lecture 19. This is equation 1, and we have just derived this expression that for a conservative force system, kinetic energy can be expressed as 2T equal to Qj dot and Pj. Pj, of course, you know, Pj is del T by del Qj dot. So you put the value here, and we are calling this as equation number, that is 2T is equal to this quantity. This is equation number 1a. Further, T is the function of the generalized coordinates and the generalized velocity. And when you open this expression, in fact, this is not like only one, Q1, Q2, and Q1. Further, Q1 dot, Q2 dot, and Q1 dot. And when we take the derivative, total derivative of T with respect to small t, the time, when you simplify this, we get in the form of summation. Of course, when you take the total derivative, we get del T by del Q1 into Q1 dot plus del T by del Q2 into Q2 dot, and so on. Similarly, when we start from here, then we'll get del T by del Q1 dot, and here it will be Q1 double dot plus del T by del Q2 dot into del Q2 double dot, and so on and so forth. We'll extend it up to n. So when we write in compact form, then it gives you the summation j going from 1 to n, and this expression star. Now from equation 1 for j going from 1 to n, if we simplify, we have these equations. Multiplying these by Q1 dot, Q2 dot, Q1 dot respectively, and then adding. So we'll get Qj dot d by dt del T by del Qj dot. We are adding these, minus this part gives you summation is there, of course. Qj dot is outside, del T by del Qj, and del V by del Qj we are taking on this side. So this is equal to 0. Okay, when we take the summation individually with each of these terms, we get Qj dot dt by d by dt del T by del Qj dot minus this thing Qj dot del T by del Qj plus summation Qj because Qj, this is in fact Qj dot del V by del Qj. This is number 2. Now we try to obtain the value of this expression here. In fact, when we simplify this d by dt Qj dot dt by del T by del Qj dot to first function, derivative of second plus derivative of first, it becomes Qj double dot, and second function as it is del T by del Qj dot. So we are getting this equation number 3. Now from this equation 3, if we take this term on one side and this term with this term here, so we get the value of this Qj dot dt by dt del T by del d by dt del T by del Qj dot, value of this, in fact this minus this. So this Qj dot has been written like this, Qj double dot has been written like this. This is the same thing. So in fact this is, we are taking in left hand side. So we have obtained value of this quantity. Now put this value 4 in equation number 2. In fact we'll substitute value of this, value of this thing. In place of that, we shall write this quantity. In place of that, here we shall write this quantity, and subsequently we'll get this expression minus this quantity is here. Now look at the situation. Summation j going from 1 to n, qj dot del t by del qj dot minus, we are combining this term and this term, both the negative terms are there, then this becomes in fact qj dot del t by del qj is this one, and del t by del qj dot d by dt qj dot, we are writing it like this, plus the last term qj dot del v by del qj is here. This is equation number 5. Now using equation star in 5, in equation star we are given the value of this quantity. In equation star we are given the value of this quantity. You can see in equation star, yes, no, not that quantity. In equation star we are having d del t by del qj dot plus del t by del qj dot qj double dot. We are having value of this quantity. This quantity is in fact here. This quantity is in fact here, because d by dt qj dot is in fact qj double dot. So this is exactly the equation star. So in place of this quantity, here we can write dt by dt. This is using star in 5. This part remains as such. This is dt by dt plus this quantity. Further, from equation 1a we are given that this quantity is equal to twice of t. So now we substitute using equation 1a, we substitute in 5a, this quantity becomes 2t. That means d by dt 2t minus dt by dt is there plus this quantity. So twice of dt by dt, we are left with dt by dt qj dot this. Now this is equation 6. Now since the potential energy is function of the generalized coordinates only, so dv by dt, when you open it, we'll have del v by del q1 and q1 dot plus del v by del q2 dot and so on. Compact form we can write it as j going from 1 to n del v by del j del qj dot. So in place of this summation, here we can put dv by dt. So when you do this, we have dt by dt plus dv by dt, d by dt t plus v equal to 0. That means t plus v is constant. So therefore we can say that the sum of kinetic energy and the potential energy is constant for a system of conservative forces. This principle is known as principle of energy. So that is it about this lecture. Thank you.